Hi again, guys. This is me just going to go through those questions 1 and 2 that I set you on Monday, because they are a bit tricky to try and do from your home from scratch. So just to quickly reiterate what we've just done with the refracting telescope. You've got an objective, you've got an eyepiece. They're separated by the distance of the two focal lengths. So basically this is a lens, you know, like a kind of curvy glass lens. If we were in the lesson, we would have shown you that. And each lens has its own focal length, which means that when light comes in parallel, or what we say infinity, it focuses at that particular point. So that's that point. Can you see? And so the distance from there to there is the focal length. Okay. And then the eyepiece is another lens. Now the eyepiece focal length is normally smaller because it affects the magnification, the ratio of these two. So this one's normally smaller. And again, it just depends on the lens. So this lens might say be 5 centimeters, 2 centimeters, whatever it is. Now, the thing that you're looking at, or the object, comes in, I put image there, it should be the object, comes in at a certain angle. And this angle, and this is kind of like along, what would you call it, on the surface. This angle here is the angle that it comes in at. If you just looked at it without any telescope, that's what it would come in at. That's the alpha. Now the telescope magnifies the angle in which the light comes in at and makes it look like it comes in at a bigger angle, and that's beta. So what I explained in the last clip is that if you put your eye here, it sees the light coming from a point over here, which is like infinity, but it's a lot bigger. So basically, we're talking about generally blobs of light. So the blob of light is bigger, and it's coming in now at an angle beta rather than alpha. And the way in which it's magnified is to do with the focal lengths. So the focal lengths here, so the magnified angle over the original angle without a telescope is equal to the objective focal length over the eyepiece focal length. Okay, and that is called the angular magnification. Now, bear this in mind with the question that we are about to do. So, the question says, the telescope is used to observe a planet which subtends an angle of 5 times 10 to the minus 5 radians. So this is the angle which it is coming in at. Is that okay? So I'm assuming we've done... Oh, I've missed out. Sorry, I've missed out a bit. This is one part 2, but I've just realised I've missed out a part 2, which is asking for the angular magnification. So the angular magnification is just going to be F0 over Fe, which is 2.5 over 0.02. We get that from the question, which is equal to 125. Is that okay? And so for the next part, it asks you to work out the angle subtended at the eye by the final image. The angle subtended at the eye by the final image. So they're asking for this one, and they're saying that it's coming in at this one. So that one is alpha. So that one is alpha. Now, I've told you in the previous clip that this is also equal to beta over alpha. So we can just say that beta over 5 times 10 to the minus 5 is equal to 125. Rearrange, and beta is 6.2 times 10 to the minus 3. Can you see that? Sorry, 6.2 times 10 to the minus 3 radians. Okay, so that's how you do the first question. Now, the second question, again, it asks you to draw a telescope, and I've shown you how to do that. But the next bit might seem a little bit harder to you. So 2B, it says the distance between the two lenses, and now I've noticed that some of you have been able to do this already, so if you can do this, you can perhaps just fast forward this bit for yourself. But it says the distance between the two lenses was approximately 3.5. So going back to this diagram here, the different distance between those two lenses is 3.5. So that means F0 plus Fe is equal to 3.5. It also says that the angular magnification is 100. So we know that F0 over FE is equal to 100. So we can say that F0 is 100 FE, and then I can substitute it into that equation. So I've got 100 FE plus FE equals 3.5. So 101 FE is 3.5. So FE is going to be 3.5 divided by 101, which should give me 0.035 meters. Okay, and then we know that F0 plus FE is equal to 3.5. So F0 plus 0.035 is equal to 3.5. Rearranging that gives us F0 is equal to, well, 3.5 take 0.035. Which is, if I've got it on my calculator, if you want to be precise, 3.5 take 0.035, which is 3.465 meters. Okay, so that's that one. Now the next bit of the question is using the small angle approximation. So this is part 2. So part 2 is using the small angle approximation. It says, using the telescope, Huygens discovered Titan, a satellite of Saturn, at this angular magnification. The image of Titan subtends an angle of 4 times 10 to the minus 3 radians when it is approximately 1.3 times 10 to the 9 kilometers from the Earth. Now, this is the image, it says. So this is a bit that you have to work out. Is it alpha or beta? If it's the image, then it's the one that's magnified by your eye. So it's beta. Okay? So beta is in fact 4 times 10. Sorry, make it a bit straight for you. 10 to the minus 3 radians. Now, you have to use, I'm going to turn over for this one bit actually, sorry. 4 times 10 to the minus 3 radians is equal to beta. And we know, hang on, let me just get that right. We know that the magnification, we know that beta over alpha is equal to 100. Okay, so we can work out alpha. Alpha is going to be beta over 100, which gives you 4 times 10 to the minus 5 radians. And then, so that's the alpha. That's the, let me go back to this one again. So that is this light coming in here. Okay, now on the PowerPoint I showed you yesterday, I said there's this weird thing called the small angle approximation. So we are saying that this angle now is 4 times 10 to the minus 5 radians. We're saying that this distance is 1.3 times 10 to the 9 kilometers. And this is what the question is asking you to find, which is the diameter of Titan. So basically, if you look from one side of Titan to the other, and it's coming in at that angle, you want to work out this. Okay, so what I said yesterday in the small, or what the man said yesterday on the YouTube clip, is that x over 1.3 times 10 to the 9 is the same as the angle, assuming the small angle approximation. So basically this over this, because these two distances are roughly the same, this over this is equal to that angle. And that's just a trick that they use in astrophysics a lot. If you want to, you can use trig and try and solve it that way, and you'll find you'll get the same answer. Only if it's in radians, by the way. And I'm going to keep it in kilometres just because I can, and it makes life easier. It just means that my answer is going to be in kilometres. So that is going to be equal to 4.5 times 10 to the minus 5. So x is going to be 4.5 times 10 to the minus 5 times 1.3 times 10 to the 9, which gives me, just do that on your calculator, 5.2 times 10 to the 4 kilometres. Okay, so this is, can you see that? So this is just the trick of using the small angle approximation. That's that clip that I showed you. So basically, if something's a long way away, that far away, and you're using a triangle like that, and it doesn't really matter if it looks a bit like this, it still works, because it's kind of assuming that that's kind of like a small arc of a circle as well. So if that was 1.3 times 10 to the 9, or that was 1.3 times 10 to the 9, it works the same. Is that okay? So it's just something you have to do with astrophysics, or something that works with astrophysics. For you clever mathematicians, you will understand that better. Okay, so I hope that helps to explain how to do those 2 questions. I'll upload the mark scheme as well, and I'll try and put some other YouTube clips that might be useful on as well. Okay, thanks, bye.